It turns out if you ask a large language model to write you a piano nocturne in Music XML, it doesn't make music. It has a panic attack made of angle brackets. This entire mess is 4 measures, like your left hand goes pa, 4. Well, I got annoyed and did the only reasonable thing. I built an entire programming language so my robot could write Chopin without exploding. And then I fine-tuned 6 different large language models on it. For a class project, for fun. I am not well. LLMs already know a ton about music. Ask them what a Neapolitan chord is and they will happily lecture you. But then you say, cool, now give me an actual score in symbolic format, and they just start screaming in markup. The standard formats for symbolic music, it's the classic 3 bears problem. Music XML is like, here's the entire engraving pipeline, good luck finding the actual music in this. LMX is like, here's 3 tokens, please reconstruct all of Western harmony. What I wanted was something in between. So I built a DSL, a mini programming language, where the score is literally a program. I was like, LLMs are supposed to be good at coding, right? So let's make music into code. This is a typed programming language. We can also use the type checker to enforce musical grammar. Like, note durations in a bar have to add up to the length specified by the time signature, and if they don't, the type checker yeets your composition into the sun. Same for notes being in the scale specified by the key signature. You might be thinking, Corinthia, that's great and all, but how can an LLM write in this language if it's never seen it before? Yeah, how the do I get any data for this thing? I wrote a compiler to convert all the Music XML that's out there into my new DSL. It chews through the Grandstaff LMX corpus, reconstructs voices and scales, and spits out about 41,000 little type measure modules. And by the way, this whole compiler was vibe coded. I was like, Codex, I need a compiler from Music XML to my bespoke music DSL. And it was like, cool, here's 1,000 lines of Python that passes all your tests and works on the first try. And I was like, oh my god, the machines really are going to take over. And I threw 6 open-weight LLMs at my new dataset. 2 Qwen 3 models, 2 Gemma 3 models, GPT OSS 20B, plus a DeepSeek R1 Distill Baby. Each one sees the same music in 3 flavors, Music XML, DSL, and LMX, so we can measure their performance. The results are really interesting. First of all, as you can see here, the tokenized sizes of each dataset are consistent with our Goldilocks theory. Music XML clocks in at a whopping average of 13,000 tokens per sample, while LMX is comparatively tiny at about 500 tokens per sample, and the DSL sits somewhere in the middle at about 1,600 tokens. How do the models do when we train them on all this data? Well, as you can see, a pretty consistent trend emerges across all 6 models. Music XML scores the lowest validation loss, while the DSL sits at about twice the loss of Music XML, and LMX scores about 5 times the loss of Music XML. It might seem counterintuitive, since it seems like the models are doing the best at learning Music XML, but because Music XML is so bloated, the information content of each token is relatively low, and so the model can score a pretty low loss just by learning to close all the XML tags it opened, without learning any of the deep musical structure. But there seems to be this fundamental trade-off between verbosity and learnability, but is there some way to quantify this? Well, I did a bunch of math and came up with this formula. The W term in this formula is the one to pay attention to. It tells you how much you need to weight loss relative to token count in order for a representation with a lower loss but higher token count to come out on top. If we calculate this value for our 3 representations, we see that the DSL outperforms LMX even for a relatively low weight value, while Music XML requires significantly higher weight values to outperform LMX and especially the DSL. So yeah, Goldilocks confirmed. Also, because the DSL is an honest-to-God programming language, we can do a lot more than just throw it at an LLM and hope it learns it. For instance, we can mask out different parts of a score while keeping their types intact, and then ask the model to fill the hole with music that type checks. Train our model further on this kind of semantic hole-filling task after initial fine-tuning, we can drive the overall loss value down even further. Now for my next trick, I push this idea even further by doing reinforcement learning using the type checker output as a reward signal. Basically, I had 2 versions of the model try and complete the same semantic hole-filling task from before. If it doesn't type check, the model gets told off. If it does, it gets rewarded. By doing this, we can see a clear upward trajectory in the model's ability to follow the musical constraints encoded in the type signature of a code generation task. But I bet by now you're wondering, what does any of this generated music actually sound like? Well, here's one example. I provided 2 different fine-tuned versions of the Qwen 3 model with the first 4 bars of a nocturne I composed, which sounds like this. And asked each of them to follow it up with 4 more measures. And these were the results.
I successfully bullied an LLM into writing somewhat okay music, and yeah, that's my video. Like, subscribe, hydrate, remember the robots are coming for us.